Hello again. For today's lab experiment, we are going to be looking at what's called maximum power transfer. So we have basically two parts of the circuit. We have sort of the internal part of the circuit, and we have what's called the load. And the load is the useful portion of the circuit, or the portion that's being used for whatever appliance you're designing or you're building. And so everything with physics ultimately comes back to energy. So we're trying to maximize the power that gets delivered to the load. And it turns out it depends on the resistance of the load in relation to the internal resistance, whether the resistance from the power source or whatever is going with it. And so we're going to look at that relationship. And that's going to be the objective of this lab experiment. So what I'd like to do is summarize how this experiment works. So the main thing we're going to talk about is power. That's the energy delivered to a circuit or to the load per unit time. And a watt of electrical power is the same amount of joules per second as a watt of mechanical power. So it's important to understand that. And power is equal to the product of current times voltage. It's also equal to IR squared, or current times the square of the resistance. It's also equal to delta V squared over R, so the voltage divided by the resistance. Voltage sources have a non-zero resistance, meaning there's always some degree of internal resistance. So when you did the EMF experiment and you measured the voltage across the resistor, given the same output voltage, you measure the voltage across the resistor for 100 ohms and I think 1,000 ohms. And your voltage across the 1,000 ohm resistor turned out to be higher when they were connected in the same circuit. And that's because the greater resistance is going to take a greater share of the potential difference. And that the remaining potential differences lost inside the internal resistance of the power supply. So all power supplies have some internal resistances. If your external resistances are large, you don't need to be concerned so much about the internal resistance. But if you're interested in maximizing the power that gets delivered to the load or to your external resistance, you need to keep the internal resistance in mind. So let's look at how that works. So suppose the EMF source has a resistance small r and the rest of the circuit has a resistance capital R. So you calculate the power delivered to the load resistance. So that's the current multiplied by the voltage across the load, which is equal to I squared R. R is R is the external resistance, and I squared is the total voltage divided by the total resistance. That comes from Ohm's law. So the voltage out of the power supply divided by capital R plus small r, and you're squaring that term. And so in order to find the maximum, the value of capital R that maximizes P, you have to take the derivative of P with respect to R and set that equal to 0. So that's basic calculus. You maximize the derivative, or you maximize a function when you set its derivative to 0, possibly minimizing it as well. But as it turns out, in this case, you're maximizing it. So you apply the product rule, or rather, I guess it's the quotient rule, rather. And so you get the derivative with respect to capital R is equal to the voltage over the total resistance squared minus 2R times the voltage squared divided by the total resistance cubed. And you set that equal to 0, which means you multiply both sides by the total resistance cubed and divide by the total resistance squared, and you get capital R plus small r minus 2 capital R is equal to 0. And so what you get when all is said and done, it simplifies very nicely to small r is equal to capital R, which means that the maximum amount of power gets delivered to your load when the external resistance equals the internal resistance. So if the objective is to get as much energy as possible out of your power supply, you need, or the maximum amount of power out of your supply, you need to make sure the load resistance is the same as whatever internal resistance that you have. So what we're going to do is connect, in the procedure, is connect the power supply to a known resistance. And so I used a variable resistor for that. And then verify that the power is maximized when the load resistance matches its value. So this is called impedance matching. So we're set up an external or an internal resistance, small r, of 270 ohms. There may be some additional resistance inside the power supply. So what we do is we go through a fairly lengthy procedure of, we have a second variable resistance that we're going to vary. That's going to be capital R. So the first variable resistance we keep set at 270 ohms. So that's small r, or that plus the internal resistance of the power supply is equal to small r. And then capital R we're going to vary. We start at 20 ohms, do 20, 40, 60, 80, and 100 ohms. We measure the current, and we measure the voltage as well. And we use those to calculate the power across the resistance capital R. And so after we do 20, 40, 60, 80, 100, then we go from 100 to 500 in 10 ohm intervals. And then we go from 600 to 3000 in 600 ohm intervals. So we're setting the voltage to 1.5 volts. And what I forgot to do was measure the voltage at different values to make sure it's not changing slightly. And it turned out it didn't change slightly. I measured at the very beginning and at the very end, and it didn't change significantly. But you're going to calculate the power going across the load two different ways. The first is the current, which you're measuring, multiplied by the voltage across the load, which you're also measuring. And then also by the square of the voltage across the load divided by capital R, which is the resistor that we're varying. And then we're going to make sure those values agree. And they should agree fairly closely, but comment on how well they agree when you're writing up the lab report. And then you're going to make a plot of the load power versus the load resistance. And you should, within 10 ohms, get a value for the load resistance at which the power peaks. And that should correspond, again, to 270 ohms plus the internal resistance of the power supply. So one hint, in case you're not aware of it, is that when you're doing calculations, you can do the calculation once algebraically in Excel and then use fill down to do the entire column. And that will save you an awful lot of math. And so you can do that for both power columns, and then you'll be asked to make your plot. And then do you get the maximum power where you think you're supposed to get the maximum power? Now, you're not going to need a linear fit for this particular graph. But again, is the power maximum more or less where you think it's going to be maximum? And what can you say about the internal resistance of the power supply? So that's all you need for this experiment. And so there are, I think there may only be one video for this experiment, or for the procedure part of this experiment. So if you have any questions about any of the steps, once you look at both videos, don't hesitate to ask or email me and ask for help. Okay, thank you again, and I will see you soon.